Welcome back. You've just finished hydride nucleophiles. And so we've worked our way, and now we're on the final section of the aldehyde ketone reaction chapter, which is how they respond with carbon nucleophiles. That's what we're doing today. And so that's a very exciting one because the word carbon nucleophile means we are going to make a bond with carbon. So carbon-carbon bond, that's a big deal. All right, so as we embark on carbon nucleophiles, we have to know how to make the nucleophile first. So you're going to usually start with something simple like an alkyl halide, then convert it to something that, as we all know, is actually an electrophile, right, from SN2, and we need to convert it to a nucleophile. But first we're going to kind of understand what we need in order to make carbon nucleophilic. So we're used to seeing carbon, for example, like I said, alkyl halides. We're used to seeing carbon. Let's look at like a typical alkyl halide. We're used to seeing carbon act as a delta plus, and that would mean it was an electrophile. Or hey, what about this chapter? These are electrophilic carbons. We need a nucleophilic carbon to attack this particular electrophile carbon. How do we get those nucleophiles? We have to somehow get the carbon to have a delta minus on it so that it can attack a delta plus. So remember this previous section, metal hydride reducing agents, they were all hydride nucleophiles. So remember that's thanks to the fact that we're not used to thinking of hydrogen that way anyway, as well, because up until this point we usually had hydrogen on something that was more electronegative. If we attach it to one of those metals, however, we saw we had this dipole that was the opposite of what we're used to seeing, and so we had a H minus nucleophile. Okay, so that's the way we're going to use that same logic to achieve a carbon nucleophile. So notice here we have the R group starting with the carbon bonded to a metal that is actually less electronegative than carbon, allowing our dipole to put the delta minus on the carbon, giving us the carbon nucleophile. Okay, so versus those are carbon electrophiles. Okay, so when we have carbon bonded directly to a metal, we call this an organometallic reagent. Organo for the carbon, metallic, of course, for the metal. And there are lots of them out there. That's its own special subfield of organic chemistry. But there are about, I'd say, half a dozen that rise to the top that are used very frequently. You're going to learn about half of those now, and then later, and those are the ones that have been around many, many decades. And then some are more recently developed. In fact, the scientists are still doing research today in some of those cases, and that's actually a later section where we'll learn those. So learn half now, half later. And that later section's near the end of the class. So we're going to focus on sort of the bread and butter first, the classic cases, before we get to some of the more recent cases. Okay, so the important categories of organometallic reagents we're going to look at, and some we've actually talked about before. The first will be called organolithium. So an organolithium reagent with, you guessed it, an R group, a carbon chain attached to lithium directly. That allows us to have the delta minus, delta plus distribution we're looking for. And look at what's going on here. We had to make this. Where do we make this? An alkyl halide. So you don't just go and say, I'm going to throw, if you're doing a synthesis, for example, I'm just going to add whatever organolithium I want. Usually you're asked to make it first instead of buy it. So you make it from an alkyl halide, and we all know how to make alkyl halides if we had to do that. And then from there, how do we make it? We add lithium. And then notice there's two. One of them goes here, and the other one whisks away our leaving group. So we get a salt. And that is not something we are going to draw every time. I'm just drawing it so that you are aware of why we used it. That's our nucleophile there. So we're not done. We haven't even done a reaction yet. I'm setting you up for the next page. So we use this to attack our carbonyl soon. But we're going to kind of see all the different types first, and then we're going to start attacking carbonyls. So we're just getting the reagents ready. Okay, so that's one way to get a reagent. The other one is the well-known, the one that I cover in Organic 1, and I cover it again. So nice, I cover it twice. The Grignard reagent, named after Victor Grignard. Now, this one uses specifically magnesium instead of lithium. It does the same thing. Really does. I mean, you're not going to really use them for different purposes. So just know you have two different choices, or if you see one or the other, no, they do the same thing. But it's a little different mechanism. So the magnesium doesn't displace the halogen, it inserts in between them because magnesium makes two bonds. Lithium only makes one. So magnesium needs to have another bond there, and so this is magnesium to start, 0 to start with, but once you get, it likes to be the +2 oxidation state, so it inserts there. And so this is actually called insertion. That's the mechanistic step. There's no arrows for that step. So in those organometallic mechanisms, the arrows aren't actually drawn. The words are written to describe what happens. So that's called insertion. This solvent, CH3CH2,2O, is a very common solvent. That's diethyl ether. And so that answers that question right there below. So it actually is important because it helps stabilize our Grignard reagent. So I'm going to circle this. I'm going to note our dipole. Now we have our carbonucleophile ready to go. I'm going to write the note here that I wrote above, used to attack C double bond O, and this is what's called the Grignard reagent. Okay, so back to that solvent. What's going on there? So we have kind of a reactive carbon, and we don't want it to react too soon. So notice that delta minus is on carbon, delta plus is here. So you can actually stabilize that reagent with the solvent nearby. It's important it's not protic, and we'll get to that soon. So remember that oxygen has the delta minus, delta plus there. You could get that intermolecular force. So it stabilizes the reagent, and it'll associate all over, make like a little cage. So different ethers are chosen for this. Diethyl ether is very common, but other ethers could be chosen as well, sometimes even THF. Okay, finally, we're going to take our organolithium. Look familiar? This is from step 1. So you start with organolithium. So that was the result of number 1. And we're going to add copper iodide to insert the copper and get organocuprate. So this is called organocuprate reagent. It has a name, of course, a lot of them do. It's also known as the Gilman reagent. Gilman reagent. Okay, so what's going on here? So copper is making the 3 bonds. It's in its +3 oxidation state. We used 2 R groups. That's balanced. We're actually trying to balance an equation for once. But since we're not going to do it every time, but I want you to see what's happening with the rest of the pieces. So because we are going to use 2 organic substrates per 1 copper. So what happened to the iodide? So it went off with, what do you think? Well, we had 2 lithium and only 1 is represented here, so it went off with the other lithium. So I'm going to circle the important piece. That's our byproduct over there, the lithium iodide. I'm not going to draw that again, probably. Our delta minus is on a carbon, delta plus is on the metal. This is our carbon nucleophile, and I'm going to use the same phrasing. This is our Gilman reagent, and we use that to attack our carbonyl. Okay, why are we learning 3 different carbonyl reagents? We're actually learning more than 3, but 3 organometallic carbonyl reagents. So 3 things that can attack a carbonyl that are also organometallic. Why? Has to do with the fact that they're not all equal. They have different reactivities. And so we're going to rank them and take advantage of that reactivity. And sometimes that will help us out, like it has before, with achieving the results we want. Okay, so in order to understand the reactivity, we have to understand which one's more attracted to the carbon. So in other words, if we had all 3 in a pot and we have our nucleophile, all 3 nucleophiles were to attack our carbon electrophile, who would get there first? Who's more attracted to that delta plus? Well, whoever is more attracted to the delta plus would be the R with the biggest delta minus. How do we know who has the biggest delta minus? It's whoever has the biggest dipole. So we have to look for the difference in electronegativity. So that's not a value you might have offhand, but looking at a periodic table or looking at the values, I will tell you the electronegativity of copper is greater than the electronegativity of magnesium, which is greater than the electronegativity of lithium. Okay, that's not reactivity yet. That's the electronegativity. Let's put a small delta plus on that metal. So very electronegative metal, smallest delta plus. However, if I have a less electronegative metal, then it has a bigger delta plus. All right, so there's no number that we can associate with it. We're not going to spend our time calculating that, but there is a difference because they do not have equal electronegativities. Now, so we're just going to do that qualitatively. So knowing that their biggest delta plus comes from the lithium, that means that the dipole is bigger, right? So if the dipole is bigger, then this is more reactive. Because remember, non-polar bonds are not reactive. Very polar bonds are very easy to break, very reactive. So this is the most reactive, the one with the copper. The one with the lithium is the least reactive. The one with the lithium, sorry, is the most reactive because we have the biggest delta plus. With the copper is the least reactive. Let's draw that out just to keep it clear, because once you look at a trend, for one thing, it's not the same as looking for another. We're looking at electronegativity, now let's look at reactivity. So just to make it extra clear, so ranking is a really common type of homework test problem, ACS problem, etc. Just to make sure it's very clear that we are comfortable with what we're ranking, it's good to overly annotate it. Most reactive to least reactive. Not just because it's a common test problem. In real life, we kind of like to rank things too. Which one is the best out of a series to use? Okay, so most reactive, we decided the biggest delta plus would be the most reactive. So that would be the organolithium. That would be more reactive than the middle one, the Grignard. The least reactive would therefore be the Gilman, R2CuLi. That's because the metal that it's attached to is the most, so I'll phrase that another way. This is attached to the most electronegative metal. Therefore, the electronegativity between copper and carbon isn't as big, and this is the least electronegative metal. Okay, so we can exploit that reactivity at times to our advantage. And so that's why we want to keep that in mind. Okay, so drum roll. Here's the punchline. Are you ready? We get to actually use the reagents. We've not been doing that yet. We've been just going over the different reagents. We spent that whole page and then ranking them so we know what they do. But now we can kind of apply this as a generic template. So we're going to lump the Grignard and the organolithium together most of the time. Sure, one's a little more reactive than the other, but for the most part, they do the same thing. So don't concern yourselves over too much over that. We're going to let the Gilman be kind of the outlier. Because they will actually give us different products sometimes. But in terms of reaction speed, different results. Reaction product, not different results as far as this class is concerned, okay? So these will be the same. That's why they're practically interchangeable over the arrow. So we have our aldehyde or ketone. We had our organometallic reagent. It's already been prepared and ready to go. So remember, these came from alkyl halides at some point. Now, what do they do? So they're carbon nucleophiles. They are going to do the same thing we've been doing, attack the carbon electrophile. So take your arrow and attack with either one of those bonds. And it's always the bond to the carbon, right? So attack straight to the carbon. Open. And we have, go right there. Black. R1, R2. New R3, yay, that's the exciting part. O minus, because we opened. So it's attack, open, and then step 2 is the protonate, right? So the mechanism's the same, just a different nucleophile. Very exciting nucleophile, by the way. Say that here. You're making a carbon-carbon bond. So I always do this when we make a carbon-carbon bond. Wow. That means you can grow your carbon skeleton. There's not a lot of reactions to do that, so when you find one that does, it's really good to kind of commit that to sort of that section of your brain where you say, okay, I need to grow my carbon skeleton in the synthesis. Here's my little toolbox for that section. Okay, so protonate is the workup part. I'm not going to show the mechanism for every protonation anymore. I think we all know what's going to happen to that alkoxide. It's going to become an alcohol, right? So we get our alcohol. Remember, that's prochiral to start with and chiral to finish with. So watch out for the formation of enantiomers or even diastereomers if the stereocenter was already present somewhere else. Okay, let's do that with some real R groups that are already defined there. We'll do a organolithium, then we'll do an a Grignard, and then we'll kind of mix it up. Okay, so we want to be able to maybe condense the mechanism just to predict our product. We're not going to draw it every time, but you know, attack, open, and then you imagine protonating. So that's going to give us ethyl. Is it? Oops, that's kind of an ugly ethyl. Ethyl's attached to that carbon. Methyl's still attached to that carbon. O minus got protonated to OH from step 2. And new group is isopropyl. And this is racemic. I'll put plus or minus, or you could draw the full set of enantiomers, right? So don't forget that's what that means. So remember that equals, just in case we're not comfortable with that. So plus, so you might see your answer keys or your answer choices written out as well. So those are equivalent ways to write that. You should be comfortable with both. Okay, Grignard, same story. Attack, notice where my arrow's coming from. Starting in the middle of that carbon bond. Attack, open. And I'm not even really supposed to do the mechanism, we're just drawing the products, but a little mini mechanism doesn't hurt. It only usually helps. So I attacked open, that would be an O minus, but step 2 was protonate. So I'm going to do that now. I have an H, because it was an aldehyde, and now I have a new group, which is the ethyl. Also, chiral. All right, so now that I think we're getting the swing of it, let's do one more. Okay, notice we have 2 functional groups. alcohol and ketone. Now, of course, an alcohol is not an electrophile, so we would attack here, but there's a problem. Just when we think we're getting the swing of it, this is a big fat no reaction. Something's wrong there, and clearly the only difference is that we have an alcohol present. So that has a lot to do with it. Okay, so we're going to have to follow up on that because alcohols are a very common functional group, and they're not allowed to be present while we do an organometallic reaction. Why is that? Well, think about what we're doing. We're using carbon as a nucleophile. And recall that nucleophiles are also usually very strong bases. So what's the problem with that? If we have an alcohol, a nucleophile, aka a base, will devote all its time and energy to taking off that proton. So it's not that there really wasn't a reaction, there was not the desired reaction. So the reaction that was up there was a simple acid-base reaction. I might even be a complex acid-base reaction because that was a complicated base to use. That Grignard reagent you spent your time making is not ever intended to be used as a base. So alcohols cannot be present. So there's two reasons we can have a problem with Grignards. So, or any other organometallic for that reason. So it all comes down to having a protic reagent or solvent present. So two ways it could go bad, and we want to watch out for that. So this is a real life thing. If you're in the lab, the reaction, if it's not performed using anhydrous conditions, the reaction won't happen. So in the lab, most of our reactions we'll do like open to the air, stir, right? Nothing special. Put a stir bar in there and start mixing everything. So let's say this is our Grignard reagent, there's our ketone. Water is inherently there. Water's everywhere. You have to get it out, actively try to get it out. It's in the air. We have a % humidity associated with our air. So water is there unless you take a lot of measures to get out. And that's why when I'm in the lab, I have a big pet peeve about caps being left off of bottles, because water just, you can imagine it just flowing in there and destroying any reagent that's supposed to be kept as anhydrous. So this setup would not work for a Grignard. This is not anhydrous. This would be more appropriate, one of many ways to allow it to be anhydrous. So what you'd have to do is you'd have to acquire a great amount of skill to set this up properly to get this reaction to work. In fact, prior to even the setup, the glassware would be flame dried. You would actually see the water condensation escape, and you would know it's working. You're drying your glassware. And then if you don't set it up right that day, even in grad school, we left it in the oven and at a high temperature just to keep the water off of it. Quickly set it up with like hot mitts on, and then we can't have air. We would evacuate the air, fill it in with an inert gas. Usually in the plumbing there was inert gas like argon or nitrogen, but if there wasn't, we'd have a separate tank, and you might even see some reaction setups with balloons to keep that in. So that would be where that would come in. So we'd have to have an inert gas, nitrogen or argon. And that's usually even kept on like a filter that keeps water out and oxygen. So things can be oxygen sensitive too. So notice it's all closed off. There's a vent usually to the like a bubbler, just so it doesn't build up pressure, but that's like the basic setup. So if you're not careful in the lab, you will have no reaction with Grignards. They're very sensitive. The other possibility of no reaction is this one we saw here. This is no reaction. A reagent added to a, this is what was on the previous page, a protic substrate. It just won't work. So the reaction that actually happens instead is, oops, let me get a better arrow there. Deprotonation, and that clearly was not our goal. So that doesn't count as a reaction. So it's safe to say no reaction. So does that mean we can never, ever use Grignard or any other organometallic, Gilman, if a reagent has got an alcohol present or a reactant has an alcohol present? Of course not. Chemists always find a workaround. So let's go through the clever workaround. So let's think through what our target molecule was supposed to be. We want to end with the methyl alcohol, because notice the methyl came from here, right? Okay, so if it attacks the carbonyl only and doesn't get all distracted by the protic alcohol, we'll be fine. So the one way we can get this to work is sort of like this masking disguise technique. It's called protecting groups. It's a big strategy in organic synthesis. So we're going to protect, that's a technical term there, protect the alcohol so it will not interfere with our Grignard reagent. There are a lot of protecting groups out there. On my bookshelf in my office, I have a fat book called Protecting Groups in Organic Synthesis, and that's still not exhaustive. But we're going to look at one really well-known one, and that's the only one we're going to really focus on this semester. TMS chloride. So we've used that before because it could actually turn it into a good leaving group. But if you're not trying to attack that carbon with an electrophile, it also turns it into something that doesn't look like an alcohol temporarily. And the good news is, this is the new part, we're going to learn how to remove it and go backward. So it's kind of like putting on a mask and taking it off. Okay, so let's write out our synthesis, our complete synthesis this time. We're going to have to protect. So first, we take our starting material. Then we, oh, and by the way, TBAF. What is that? Tetra, butyl, ammonium, fluoride. So TBAF is specifically used to take off silicon-related reagents. So in case you forgot what TMS is, so this is TBAF. In case you forgot what TMS is, tetra, methyl, silyl. Okay, so TBAF looks like this. It's an ammonium salt. Butyl's on the making up the ammonium. And then there's a plus there and the fluoride minus. Now, this works because silicon and fluorine love each other more than oxygen and silicon do. So previously, this is a silicon-oxygen bond going on here. You throw TBAF there, it competes with the oxygen, and the oxygen loses. So the TMS goes off with the fluorine, and you get back your alcohol. Remember, we do usually need some sort of base. It's often pyridine in order to just take that H off first, and then it's ready to be attached to the TMS chloride. Or NaH is another one. So let's do that. Let's do NaH for this synthesis. So step one, let's depronate NaH. That's our base. And then step two, we'll do TMS chloride. So step one, I won't show, it's O minus, acid base. Then the O minus attacks the TMS, kicks off the chlorine. So this isn't a mechanism, this is a synthesis, which is why I'm not showing the mechanism, because that will just make it hard for us to see the big picture. But it doesn't hurt to go back and write it yourself as a study point. All right, TMS. So this is introduced back in Organic 1. What we're using is a protecting group now instead of trying to make a good leaving group. All right, so now the alcohol is in disguise. No one knows it's an alcohol. We're safe to add our Grignard. So our Grignard was, actually it was an organolithium, methyl, CH3Li, followed by a water workup. That leaves this alcohol in disguise alone. And we have our methyl alcohol here. Take off the protecting group with TBAF. And we are at our target molecule. Which is always a happy moment, right? Reach your target molecule. Okay, so when you get stuck because you want to do a synthesis that has something there, there's often usually a workaround. All right, we are going to do the next carbon nucleophile, which is not organometallic. It's actually cyanide as a nucleophile. And you may have, I'm just putting up this old reaction that's, Chem 60 level, just HCl, NaCl, it's basically double displacement. H can go with Cn plus NaCl. And this is a famous reaction because if you add acid to sodium cyanide, you get hydrogen cyanide, which is a very toxic poison. But the sodium cyanide is not a poison. So it's not toxic. This mixture is not toxic unless it makes the HCN. I personally wouldn't want to chance this in the lab because inevitably some of it will get made. Wouldn't be my favorite go-to, but it's been done. And the idea is that this will eat up that mixture and avoid forming that. So instead of forming the HCN, the CN attacks the carbonyl. So we can go like this, woo, attack. So it doesn't make the HCN. I'd be wary of believing it made absolutely none, but you know how it goes. I'm going to skip all the way to the protonated version. So you can actually extend your chain by one carbon only. So if you see this new nitrile added to a carbon and you have an alcohol present, you must have used this reagent, NaCN and HCl. It has a name. This is called a cyanohydrin. Because you made basically like a hydrate, only one of the OHs is a CN. So while I was, I'm a little chicken of doing that, apparently there's historical precedent for this working and someone surviving it even when the intention was to poison them. So Rasputin is very famous, got a lot of, had a lot of enemies, many attempted murders. It was notoriously difficult to kill. So apparently one of the attempts to murder Rasputin involved sprinkling cyanide over cakes served after dinner. Then the poisoned cakes actually had no effect on Rasputin. And it was chalked up to like superhero stamina levels, when the chemistry actually explains that that was not the case. What do cakes have in them? Carbohydrates. What do carbohydrates look like? They have aldehydes at one end. This is the aldehyde chapter. What are aldehydes? Electrophiles. What is cyanide? A nucleophile. Actually, it's a full minus charge. So this is plus and minus. It attacked. That's the CHO, right? So it's CHO means that. It attacks that carbon, and look what we get. Cyanide attached to this carbon. So this is the green carbon here. It moves down one. And it could have attacked from either side, which is why we have the collection of enantiomers, right? And then, keeping that in mind, it can cyclize, because we'll learn that in the carbohydrate section. So don't worry too much about the rest of that. So Fisher projections come back into play for carbohydrates, of course. So, but don't worry about the cyclization process. Just know that you can attack a carbonyl with cyanide as a nucleophile and get the nitrile as the new attachment, cyanohydrin. So this is a cyanohydrin. So it wasn't Rasputin's resistance to poison due to his amazing strength. It was simply the chemistry of cakes. So maybe it wasn't such a good idea, in other words, to add it to a cake. Other things that might have been more effective on the dinner table.